Hello, everybody. This is the video I promised, walking you through those two example problems in chapter 11, the shear strength. The first one we're looking at here, a dry sand sample has filled with principal stresses of 140 kPa and 244 kPa. With this information, you need to find out the friction angle of dry sand, the angle that the failure plane makes with the major principal plane, the normal stress and the shear stress on the failure plane, and determine the normal stress on the plane of maximum shear stresses. So first of all, whenever you see the principal stress over here, you know exactly that we have a sigma 1 and sigma 3, and with sigma 1 and sigma 3, and also remember like the major principal or minor principal stress plane, you're looking at a shear stress of 0 over here. So with those information, you can actually very quickly plot the MER circle right over here with a 140 and a 0 on the tall, on the sigma, and tall, and also 244 over here for the sigma 1. So that 140 and 244, the line that connects those two points are going to be the diameter of the circle. So you draw a circle or a half circle like this. That's going to be your MER circle. So after you have the MER circle, there are a couple of things that I typically do. First of all, I would like to find out the center. I would like to find the center of the circle. Basically, you do 140 plus 244 over half, and then so that 192 is going to be the center of the circle. And also, it's a good idea to find out the radius of the circle as well. So the radius is going to be 244 minus 140 over 2 right over here, and you will have a radius of 52. So that's basically how you do the circle as well. So after you do that, try to plot the failure envelope. And coming back a little bit, and we know this sand is a dry sand, so it does not really have any cohesion. So you can very confidently draw a straight line from this 0, 0 point over here, and then draw a straight line that is tangent to the MER circle you just constructed. And with that tangent, you can have a right angle over here. You can have a right angle over here. And you know that the angle that this straight line or the failure envelope with the x-axis is going to be the friction angle. So, and the first one is actually pretty easy. Use this leg over here, 52, and use this one over here, 192, and you can very easily find out your sine friction angle is going to be 52 over 192, and use our arcsine relationship, and you can find out the friction angle is going to be 15.7 degree. Okay, so the next one is the angle between the failure plane and the major principal plane. So major principal plane on the MER circle, this is the major principal plane, and that point over here is going to be the failure plane. And use the two double angle relationship. This angle here is going to be 2 theta, just because the angle going into the MER circle is going to be doubled. And use the angle relationship. If you look at this triangle over here, the straight angle, so your 2 theta is going to be your 90 degree plus that friction angle. So based on that, we can find the angle between the failure plane and the major principal plane is going to be 52.9 degree, which is 45 degree plus half of the friction angle. So next one is find out the normal stress and the shear stress on the failure plane. So basically what they're asking for is the coordinates of this point over here. And naturally you just come down here, and they're basically asking for what this leg is going to be and what this leg is going to be. Well, to find out that, we can use the previous bigger triangle because we already know the edge or the leg over here is 52, and the leg, oh no, the hypotenuse over here is 192. So you can figure out this question mark over here by a simple equation over here. So that question mark is going to be 184.8. And then you look at this smaller triangle and use the trigonometry and also the friction angle you just calculated. So you can come up with your tau is going to be your 184.8 times sine friction angle is going to be 50 kPa, and your sigma is going to be 184.8 times cosine friction angle. That's going to give you 178 kPa. So the coordinates of the failure plane is going to be 178 and 50. So that is the normal stress on the failure plane. That's the shear stress on the failure plane. So last one is the normal stress on the plane of maximum shear stress. So if you look at this Murr circle over here, and the point with the maximum shear stress is basically the point right above the center, and this point over here represents the plane with the maximum shear, and the normal stress is going to be the same as the center of the circle, which is 192. We already calculated that. So yeah, it's pretty straightforward. A bunch of trigonometry, and also make sure you understand how you make the circle using sigma 1 and sigma 3, and what does a failure mean, speaking of the relationship between that failure envelope and the Murr circle. So pretty straightforward. So okay, let's move on to the next one. This one we actually practice this a little bit in our lab. Basically, you need to understand or sort of kind of process the data that you get from a direct shear test. Direct shear test, the principle is very, very simple, but you kind of need to understand how you are able to construct the failure envelope using the direct shear test results. Dry silty sand, when it's dry, your cohesion again is going to be 0. I mean, again, it's a sand, dry sand, so very your cohesion is going to be very close, or if not 0 to 0. We have the diameter. Looks like we're talking about a cross section of a circle. Height really doesn't matter much. So whenever you have a diameter, it's a good practice to come up with a cross section area. And looks like everything is in metric. So again, good idea to convert millimeter to meter. And this should be meter squared. So with a 71 millimeter diameter, your cross section area is going to be 0.003959 meters squared. So I carry a little bit more digits over here, just kind of want to, because I just want to make sure the calculation is a little bit more accurate. So you have the normal stress, 150 kPa. So there's not much you need to do with that because if not, if they give you a normal force, you need to use that force divided by area to come up with a normal stress. And they did not give you the shear stress, they give you the shear force. So use that 276 Newton over the area, you're going to come up with the shear stress at failure. So with that 150 and 67.9, you can find the point on the failure envelope. And again, use that point and the 0, 0, because we know the cohesion 0, you can construct this failure envelope. And you can easily find out the friction angle. The friction angle is going to be, use this triangle over here and use the tangent relationship, and you can come up with a friction angle of 24.9 degree. And the next one is, if you're going to do this test again, if you're going to elevate the normal stress from 150 to 200 kPa, what shear force is required to cause failure? So still follow the same concept that if you increase this 150 to 200, and then how much is it going to be for your shear stress over here? So very simple. Your shear stress at this new vertical stress is going to be your shear stress time the tangent friction angle. You just calculate the tangent friction angle, and you're going to come up with about 93 kPa of shear stress. So, but you do need to convert that shear stress, use the area, to a shear force. So 368 Newton is going to be the answer for the second part. So as you can see, it's very, very simple. The idea of direct shear test is simple. The data processing is also pretty simple. You don't really need a Mars circle for that. But we talked about the difference between direct shear and traxel, but direct shear tend to be on the easier side for a bunch of the data processing. So hope you liked it, and if you have any more questions, feel free to send me an email or stop by my office. So, okay, bye now.